We're going to do some calculations today utilizing information that we've learned about some of these crystalline solids and how they pack into unit cells. Now, I'm not going to go through a lot of the information on the difference between a simple cubic, a body-centered cubic, and a face-centered cubic. I felt like his diagrams in the book were pretty self-explanatory. His explanation was pretty good. If you have questions on that, shoot me an email and I'll try to help you get that straightened out. But I thought most of that was pretty straightforward. So we're going to go straight into calculations. Now, what I would recommend that you do is that you get an index card and that you go ahead and get this information onto an index card that you will be allowed to use during your test. There are a lot of things in chemistry that you just have to have memorized. I mean, you have to have Avogadro's number memorizers. You know, there's certain constants that you use all the time and you just have to have them memorized. But something like this, unless you're going to be a chemist and spend your entire career working on crystalline solids, you're not going to need to memorize this. This is something that you're going to be able to, you can look this up relatively quickly. The things that you need to be able to get are how many atoms per cell there are in each simple or in each type of cubic structure, whether the simple cubic, the face-centered cubic, or the body-centered cubic. Again, this is something that as you read the book, hopefully you were thinking through it as you read it. The third one is on your own problems that you were supposed to come up with how many atoms per cell there were. And I guess I just gave you the answer. So there's a freebie for you. But do please make sure that you are thinking through that so that you know where that number came from. Okay. The other thing that you need to be able to do is I would have how to calculate the radius of each one of those atoms depending on which kind of cell that they pack into. So I would get those written down as well. Because most of the edges are measured in angstroms, you need to be able to convert that to meters. And since we normally are calculating density of these things in grams per cubic centimeter, you may find it most helpful just to convert your angstroms directly to centimeters. So here's the conversion for that. And then you're also going to need to know that one atomic mass unit is the same as 1.66 times 10 to the minus 24th grams. All right. So let's look at example 4.2, which is on page 120. Yeah, page 120. And we'll go through this example. It says at 25 degrees, the edge of silver's face-centered cubic unit cell is 4.09 angstroms. What is silver's density at 25 degrees Celsius? Okay, so to find density, we need mass and we need volume. So let's start with volume. Let's do that one first. So the volume, if I know the edge of the cell, all I'm going to have to take to do that is to cube it, and that will give me the volume. So that's going to be 4.09 times 10 to the minus 8 centimeters. All I have to do is add this piece on there to convert that. And then I'm going to cube that to give me the final volume. So the final volume is going to be 6.84 times 10 to the minus 23rd cubic centimeters. He went through a whole lot more rigmarole to get there, but the way I look at it is if you can convert angstroms directly to centimeters, it's a whole lot easier than what he did in the book. All right. Now, to calculate density, I also have to have the mass. So the mass of one atom, you have to keep in mind that that's what we're calculating here. If you look at the periodic table, you will see that the mass of silver is 107.9 atomic mass units. And you may be going, wait a minute, I thought that was grams. Remember that the periodic table gives us mass in atomic mass units for one atom. If I'm looking for an entire mole of atoms, then it's giving me mass in grams. Well, I'm working at the atomic level right now, so what I want is the mass of one atom, and that will be in atomic mass units. Then I will need to take this and convert. So with one atomic mass unit, there's 1.66 times 10 to the minus 24th grams. And so that is going to give me 1.79 times 10 to the minus 22nd grams as the mass of one atom. Okay. Now, a face-centered cubic unit cell has 4 atoms per cell. And so what I'm calculating is the density of the cell. So my density then is going to be 4 times this 1.79 times 10 to the minus 22nd grams, because there's 4 atoms per cell. And then if I divide that by the volume, 6.84 times 10 to the minus 23rd cubic centimeters. Okay, so you're going to divide that out and you're going to end up with 10.5 grams per cubic centimeter. Okay, so not too hard, right? You're going to take the edge of the cell, calculate the volume, find the mass of one atom, convert it to grams. So it's really just a lot of conversion. And then remembering how many atoms there are per unit cell for whichever particular element that you're talking about. Okay. Now, the other thing that you can do that is not in your book, but again, I'm going to expect you to know how to do this, so you want to make sure you take good notes on this. You can also take this kind of information and you can figure out, kind of go backwards and figure out in what kind of unit cell the atoms are going to pack. So this is the problem that we're going to be working. Sodium has a density of 0.968 grams per cubic centimeter and a unit cell side length of 4.29 angstroms. In what type of unit cell do sodium's ions or do sodium's atoms pack? Okay, so again, we're going to kind of take this and we're going to kind of work backwards. So the first thing that I'm going to have to do is, again, I'm going to have to find the mass of one atom. And so if I look at the periodic table, I'm going to see that the mass of sodium is 23.0 AMUs. And then just like I did before, I'm going to convert that to grams. So I have 1.66 times 10 to the minus 24th grams over 1 AMU. And so that is going to give me a mass of 3.82 times 10 to the minus 23rd grams, okay? Mass of one atom, okay? Then I need to know what the volume is because I'm going to have to use the density formula. So since I know what the side length of the unit cell is, I can then find the volume from that. So the volume is going to be 4.29. And again, I'm going to take angstroms and I'm going to convert it directly to centimeters. So it's going to be times 10 to the minus 8 centimeters. I'm going to take that value and I'm going to cube that to give me the volume. Okay, so that's going to be 7.90 times 10 to the minus 23rd cubic centimeters. All right, I know the mass of one atom and I know the volume, and I was also given the density. So what I can do then is I can use the density formula to work backwards and find out what the mass of the whole unit cell is. This is the mass of one atom, but I don't know how many atoms are in the cell. Over here, if you recall, I knew how many atoms are in the cell, so I could put that number in there, but I don't know what that number is, so I've got to find it. So my density is 0.968 grams per cubic centimeter. I don't know what the mass of the whole cell is, but I do know that the volume is 7.90 times 10 to the minus 23rd cubic centimeters. Okay, so when I multiply those two together and solve for mass, I'm going to get a mass of 7.64 times 10 to the minus 23rd grams. So that's how much mass is in the entire cell. So then if I take this mass of the entire cell and divide it by the mass of one atom, that's going to give me how many atoms are in the cell. So if I take 7.64 times 10 to the minus 23rd grams, that's in the whole cell, but it's going to be 3.82 times 10 to the minus 23rd grams per atom. When I divide that, what you will see is that that is going to give you a value of 2 atoms. And so therefore, since there are 2 atoms in it, that tells me that sodium crystallizes in a body-centered cubic cell. Okay? I did in your lesson plans give you a couple more practice problems to work like this one so that you'll get some practice on that.